Greetings, everybody. My name is Chris Neidl with Rethinking Removals and OpenAir. Very excited to bring this session to you today. This is actually a project called Epiphyte that has been in the works for some time. In fact, it was referenced last year at COP27 with our first carbon removals at COP. We talked about the concept a bit, and now we're reporting back on some real work that's been done, and we think some exciting directions that lie forward for the Epiphyte project. And you're going to be hearing from some of the core members of the team who are working on it. But just to give you a high-level view of what it is, I'll give you a provocative picture here. This is what we think is the first open source direct air capture project in the world. And it was really hatched out of the OpenAir collective and some of the volunteer members within that community that work on open source community-driven carbon dioxide removal R&D. And we've been around for 4 years, and we've had a few different projects that groups within our community have worked on related to direct air capture, related to mineralization. But this project, Epiphyte, is really the culmination, I think, of a lot of what we've learned of, as a community over the last few years. It is definitely the most sophisticated project that we've worked on. And the idea behind it is, can you start very, very small and modest and create a core design around direct air capture that can be the basis of a lot of experimentation by many people all over the world? That it's conceivable that many people could build these small units, and then collectively, in true open source fashion, can we actually go ahead and keep optimizing it at a rapid rate? Can we take it in directions through a peer production and open source model that maybe the marketplace normally wouldn't? But at least, at the very least, can we bring a lot of people's sort of creative juices and thinking focused on direct air capture and inspire more activity, more interest by a broader public? So with that, I'd love to bring on a couple of the people that have been real drivers of this project. We got David Wilson, who's really Herculean efforts over the last many months, just doing ingenious things at home and at the University of Pennsylvania in Philadelphia, where we've been building this. And then Seth Sternberg, where are you joining us from right now? Are you in Washington, D.C., Seth?
Yes, I am.
So Seth has been applying his mind to this remotely and has been really bringing a lot of his knowledge of sensors and electronics, and has just been an amazing sounding board and more for this project. And Seth and David are just two of, we have a kind of a smaller team represented today, but there's been a number of other folks, Chuck Pearson, Ling Kong, who am I missing? We've got other people who have decided to remain nameless, but have put a lot of effort into this. And again, we think that this is just the beginning. We want to publish this design under an open source license and try to build a large global community to keep evolving it. So with that, I'd love to have David and Seth just quickly introduce themselves and where they're coming from and how they got involved in the project. David, let's start with you.
Okay, I'm David Wilson. I'm in Philadelphia, and I've been involved with the OpenAir collective for maybe 3 years. I started working on a project called Cyan, and I've also been doing a couple of other projects, and then which kind of evolved into the current project, Epiphyte. And I'm a part-time volunteer on the project, and I'm an electrical engineer.
Excellent. And Seth?
Yeah, hi, everyone. I'm Seth Sternberg. I've been a member of OpenAir probably since this spring. So this is my first project. Just looking to help out however I can. My background is in software and sensing.
Excellent. Great. And what I want to do is actually just bring up, I think, as a way of introducing this audience to Epiphyte in more concrete detail than what I started us off with, is I think we should just start with the question of, okay, what exactly is Epiphyte as a built unit? And what I'd like to be able to show here, David and Seth, is just a primary basic drawing that is a version of this drawing we've been sort of operating with before we built it for a long time. And I wonder if, David, in the most simplest terms, if you want to go ahead and describe what Epiphyte is in very basic terms here, what we're looking at as a system, and then we'll show the real pictures in the video of what it's become.
Okay. By the way, for background, I should mention that the basic idea for Epiphyte came from a project called Thursday that was built by Octavia Carbon in Kenya. And they have since evolved into more sophisticated designs, but this one was presented to us and it looked like something that could be built, as they demonstrated, by a small team. And it became the foundation of the idea. So what we have with Epiphyte is it's technically called a thermal vacuum swing adsorption methodology, where in the adsorption phase, which is shown in this drawing, you blow air through basically this ductwork, and in the center is a sorbent panel that has obviously sorbent, and you blow the air through a certain amount of time, and the sorbent should ideally adsorb some carbon dioxide. And then in the next phase, Chris, do you have a desorption picture?
I might. Let me see, but we can always describe.
Yes.
Yeah, there we go.
So in the other phase, you close the dampers off, shut off the fan, and you heat up the sorbent. And when it gets hot, it releases the carbon dioxide that has adsorbed. And in the simplest terms, that's the whole process. And this is as far as our development got. But what would be needed going forward would be to add vacuum to it, which is not shown here. But the desorption process will work a lot more efficiently and give you a much purer CO2 output. If the sorbent is heated in the presence of a vacuum, and then the pump can pump the released CO2, say, into a tank or into some other device that would process it. And as part of the whole system, you can see we rely a lot on sensors to tell us how it's performing, to control it. We have CO2 sensors that are mounted on the outside of the ductwork, but there are holes drilled into the duct where the sensors are. So yes, there you go. And the sensors are enclosed in a box so that they measure the CO2 on both the input and the output. There you go. And while you're adsorbing it, you should be able to measure that the CO2 on the output side is less than on the input, which would mean the sorbent is actually capturing CO2. And then in the desorption phase, you can measure the CO2 that's being released. So you can calculate how much you've actually captured and
I
released.
think I have some images of that here, David, I believe. Is that what we were capturing here?
Yeah, so that's, I have software that is running the whole thing, controlling the temperature of the sorbent and then measuring the CO2.
Yeah. Well, just to go back a little bit further, I would like to kind of do a little bit of a tour of some of the elements that you just featured here. But as we showed that diagram, that was a sketch that David created at the beginning of this, several months ago, really. And over the last couple of months at the University of Pennsylvania's Department of Chemical Engineering, David and a few other folks based in Philly have been building this first one. And it's important for us to note, as David said, this is really just the beginning. There's a lot more to do. This is what we called our Hello World design. Could we just create a basic system where the measurement of success is that we built it, we put some sorbent in it, and we could measure however inefficiently or imperfectly it took some carbon out of the air. And that was sort of the parameters for success. But David, go ahead and elaborate on that if you'd like.
So this picture here shows it maybe a month and a half or so ago, before we've installed the CO2 sensors that you saw in the last pictures, and the sorbent panel there, which is sitting in that big slot. We've tidied up the wires a lot and run them through a panel so that it looks neater and it's a little bit more sealed from the outside air. Eventually, we're going to need better sealing than we have, because if you want to have a vacuum in there, you have to plug up all the leaks.
Yeah. Well, vacuum we'll move on to next, but let's even say this a little bit. The sorbent is the kind of the heart of the thing. And I have an image here that Seth actually shot recently. I can show a little bit of a video here, and you can see what type of sorbent did we use again, David?
It's a zeolite. It's called 13X. It's also called a molecular sieve. And it's the only one that was affordable that we could actually buy commercially. And we kind of knew going in it wasn't going to do a great job, because the people that are the experts in the field have told us that it's good it absorbs CO2, but it absorbs water even better. And what happens is when it absorbs the water, that kind of blocks all the little channels that are supposed to be collecting the CO2. However, we thought we'd be happy if it just collects a little bit of CO2. And that's what we call our Hello World demonstration.
Yeah, and as I was telling you, David, one of the things we're excited about with this is, could we build a structure, which you're looking at right here, which is called the sorbent panel, which we'll walk through in a second. And this was uniquely designed by two of our members, actually. This is one of the early CAD designs. We said, could we create this kind of structure where in the middle of it basically had a little bucket with some wires running through it that we could pour the sorbent into, as you see right here. It looks like almost like gerbil food, I think we've decided, or rice. And the wires that are running through, David, maybe you can explain what's happening there. Why are we heating up the sorbent?
Well, that's what you have to do to make it release the captured carbon dioxide. It absorbs it, that is, captures it when the temperature is room temperature, but then when you heat it up, it releases it. So the system that we hit upon for actually warming the sorbent is with these heating wires that are built of nichrome wire, which has a fairly high resistivity as far as wire goes. And when you run a current through it, it heats up. So we have, in this position, we can say that the bottom side of the panel there, where you see the screen, that's kind of the front face where the air will be blowing through. And then there are wires, and then there will be sorbent poured on top of that, and then wires placed on the other side of the sorbent, and then a screen to contain it. Then the whole thing kind of sits vertically in the chamber.
And I have a couple of other pictures here. So this was the sealing of the sorbent panel. We put it on.
That's right.
Yep, and a couple of other images of that as well. And so we said from the beginning is, can we get the most basic available sorbent and then just see if the system works as a whole? And I think, what would you say, David? Obviously not a record breaker, but it did go in the proper direction. We were able to monitor that CO2 was actually absorbed from it. And now the key is, which we're excited about, is even here in Dubai, I connected with some colleagues, and we're going to procure another type of sorbent, which looks a lot like this. It's pellets, but it's a metal organic framework sorbent, which is a lot better at not absorbing water. So we'll get that in the mail, and we'll be able to experiment with that. But a part of this project that's exciting is, can we try to go out and use this to identify what are the best kinds of sorbent for this, and certainly improve upon where we started.
Oh, by the way, one question people might have is, we have this chamber that in the middle where it flares out is 2 foot square, and so our panel structure there is also 2 foot square to fit into it, but the little pocket that holds the sorbent is only 8 inches by 8 inches. The reason we did that is basically the affordability of the sorbent, that we didn't want to have to buy enough to completely fill up that area. We put it in that small pocket in the middle, and the air should go all through there, and so you get more air blowing through a smaller place, and you don't need to buy as much sorbent.
Yep. Yeah, it's pretty elegantly designed. And, our friends at Octavia who designed Thursday, which, as you mentioned, this was inspired by, I think we're impressed by our sorbent structure, it was an improvement they thought on their prototype. So I'm pleased that the MOFs that we're going to order are not a fine powder, but rather another pellet. So it looks like we might not have to change the structure that we have to use an upgraded sorbent. So, but I did want to show a couple other quick pictures here. That right now, this is bolted, right, David, onto a cart.
Yes.
So it does have some mobility. So one of these days we can, potentially take it out for a walk and rest passersby. And did want to show a little bit of the sweat and labor here. This is Chuck Pearson, who is a long time, he's an engineer who's worked in the HVAC space, where he was able to actually apply some of his accumulated wisdom in that space to help us find some parts and think of the ways in which we could put this together. So there's Chuck working away at the build here. This is probably my favorite image from the whole process over the last few months, which is just David thinking about. Do you remember, David, what you were thinking about there exactly?
No, but the last picture that shows Chuck, it looks like he's straining. He's not faking that. That metal of the damper really is thick steel, and it was hard to cut, as opposed to the thin aluminum, I think, of the chamber.
Yeah. Great. Well, you also ran us through already the sensors, which was, I do want to give a shout out to Ling Kong, who's one of our members, who kind of custom designed this. We had the sensors, right, David? But we didn't necessarily have a way to optimally place them where we wanted to in the unit. So she designed these and then 3D printed them and then sent it to David in the mail from the Bay Area where she's based. And those worked out quite well, right, David?
Yeah, that's right. Because if you, the sensors are an SCD30 made by Sensirion, and in their application recommendations, they say the sensor shouldn't be located in the direct path of the air, because that would cause it to have an incorrect reading. So we mounted them in the boxes that Ling made on the outside of the chamber. Now the input one on the left, that was kind of tough because I had to drill through both the aluminum of the big chamber and then the steel of the damper structure, and that was so hard that I decided not to try to do that on the output one. So the output one was a lot easier. I just put that on the where you see it on the kind of diagonal part of the chamber, which, as I will show later, had possibly some I don't know whether that caused it not to be great or not, but we'll have more to say on that later.
Great. And what we can do, I think, David, is if we want to go through that, so just to kind of recap a bit on, what we've covered, is that the idea is to create a very, very simple direct air capture system that once it's introduced to the world with some documentation and under an open source license, can we get dozens, hundreds, thousands of people thinking about ways to continuously improve this and use it. And so that what's happened over the last few months in Philadelphia is the very beginning of that process. And we have some other things to still complete in order to complete this first build. And it's likely that we're going to shift it to New York City, where OpenAir started, and probably house it at NYU for some of the things that David even alluded to, the vacuum piece of it, and probably testing this new sorbent. But David, did you want to run us through some of the main takeaways, I think, that we've sort of found, and some sort of cautionary tales, I think, that you've included in your presentation? I think we can cover that right now, if you'd like.
Okay. Yeah. This is the latest picture I have of Epiphyte. So you can see that a couple of things we've done is you saw this panel before being kind of open, the wires going every which way. I put some holes in it, and everything feeds into the panel through these holes here. But then this is an electronic module that controls all the temperature sensors. And I decided to just stick it onto the side here so that makes it simpler to when I need to pull the panel out.
If I could just jump in with one thing about pulling that panel out. So one thing we did when we designed Epiphyte to try to make things easy and more modular is the dimensions of the chamber where the sorbent goes were designed to fit a typical household furnace air filter, because that way we could just get standard off-the-shelf ductwork. And it worked great, except when we designed our sorbent panel insert, we made the tolerances a bit too tight. And so sliding that panel in and out became a little bit difficult until we shaved some things off. So, that's just one word of caution for the next builders.
Don't make it too snug.
Don't make it too snug.
Gotcha.
Right, that's a very good point. So, okay, this is our main accomplishment, our Hello World accomplishment. These are the results from the sensors on the when it is in the heating phase over time. So over the course of an hour, if you look at the red and the pink traces, and the scale for them is on the left the y-axis on the left, CO2 concentration in parts per million. On the input, the left side, you can see when you heat it up, the CO2 in that chamber now goes up to about 1700 ppm, and on the right side, the pink trace, it goes up to about 800. And my theory is the reason you see a lot more coming out on the left than on the right is that's the side that when you're in the adsorption phase, the air blows through, and so it captures more of the CO2 on that side than on the output side. Now, another thing to point out, since this is the zeolite that captures water in addition to the CO2, the blue and the green traces, which refer to the scale on the right, that shows the relative humidity. We are, you can see, releasing quite a bit of moisture into the system that had been captured. Now, on the left side, the input side, the moisture rises from humidity of just over 20% to over 50%. But the thing to look at, though, is this red and pink trace. It shows that we did capture some CO2, so we can say hello world with this particular sorbent. So the next thing I'm going to cover is for the next people building something like this, if they follow the same architecture, there are some things I would recommend doing differently or improving. I've already mentioned this, so we need a better sorbent. I think I've covered what the reason for it is.
And that is the primary one, right, David? It's just the water absorption gets in the way and almost preempts CO2 absorption. That was the big problem, right?
That's right. I will say that we had to buy one bottle of this to fill up our sorbent pocket. It was a kilogram and cost like $150, I think. But with that amount, I did a back of the envelope calculation, and it looked like we were able to capture about 300 milligrams in a 1 hour cycle with half hour of adsorbing and half hour of releasing. Not great, but it's there. So the next improvement is the thermal characteristics of the panel. I think it was a great design in that these aluminum bars here are meant to be adjustable. So if you want to change the size of the sorbent pocket, you can do that. But there is a lot of metal in there. And this plate is made of solid metal, and there's a plate on the other side. And if you look at how if you can see the wires running through here, they touch a lot of metal. And it seems like, metal is very thermally conductive, and I do believe that the majority of heat coming from our heating wires was actually being parasitically drawn away from the sorbent into the metal. Because when I built a first prototype of the heating system, just on my bench without it being in contact with the sorbent panel, I saw that the wires heated up a lot faster. But even then, this shows the temperature that we measured at the sorbent wires. That's the pink one and the red one. And I tried, there's a control loop that controls the temperature, and is able just by control the processor to heat it up to 140 degrees Celsius, then 160, and then 180. And then it drops again when I opened up the chamber and blew a little air through. But you can see, though, the green wire, the green trace is how hot the sorbent is getting. So even over the course of almost an hour, the sorbent gradually heats up, not even to 120 degrees. But the panel, the frame, also gets hotter, up to about 60 degrees. But when you consider that that's a whole hunk of metal being heated from just over 20 degrees to 60, I think that indicates there's a lot of heat going into there.
So we think that blue line is basically taking away. If that blue line was flat, we'd probably have the green line would be higher, faster. Is that the idea?
That's right. We would hope the green line would go up, to the same level as the pink and the red line, which is the bare wires themselves.
Mm-hmm.
So I would recommend that this whole structure, somebody that builds an X should consider building it out of something that is not thermally conductive, plastic or even wood. The original panel that was built by Octavia was made of plywood. And so I think that might actually work better, even if it's not as flexible in the design.
You could 3D print probably that basic part there, wouldn't you think? That would probably solve the problem, the sheet there.
Yeah, I think so.
Yeah. What about if you put, for this design here, what about putting even a layer of some sort of insulation, like an envelope or something on the inside that you could then put the sorbent into, so that it's not, I guess that would be tough, wouldn't it? Because then how do you expose it to the wires?
So one of the things we talked about doing to verify this hypothesis and see where the real problem areas are is to run a heating cycle outside of the chamber, and then use, a thermometer or a thermal sensor to really get a picture of where the hot spots are.
Mm.
And
yes, that would be a great idea for.
Yeah. If we find that the hot spots are where the wires are actually touching the metal, then that's a different solution than if it's leaching heat even through the sorbent where it's not touching. Right? Then maybe it's a matter of non-conductive supports to make sure the wire doesn't touch the panel, or maybe it's some other kind of insulation or a different material.
Is that
it's worth running the experiment before we go do a redesign.
Is that easy to do though, Seth, in terms of doing that kind of heat sensing, in terms of off-the-shelf equipment?
You could use. I mean, you can get a relatively inexpensive thermal imaging camera, or you can just grab one of those head thermometers that we all use from COVID, and just take readings across various points.
Yep. And as far as designing the new thing, that's where a mechanical engineer being involved would be very helpful. It's very much an interdisciplinary effort. The ideal team would have somebody who knows electronics, programming, mechanical engineering, chemistry, HVAC, and we covered most of those in this project.
Yeah, we were lucky. It was a great team. Ling does very tiny instruments, like for medical, processes and stuff. So it was kind of an interesting team of people with a lot of different backgrounds: industrial design, material science. Okay, so those are two things. Better sorbent. We knew that from the get-go. And that was more of a sort of a supply issue. Try to get rid of this sort of thermal vampirism that's happening from the metal by replacing, doing what Seth just explained. Let's diagnose exactly where it is and then figure out a solution, but it might just be a different material for the sorbent panel itself that doesn't leach away as much heat. And then is there any other key bits of wisdom for a future builder that you would put forth?
Also, building some kind of trap door or something in this panel makes it easier to change out the sorbent. This one has to be unscrewed and kind of disassembled to get to the little sorbent pocket. But if there were a way, like a hole with a lid you could just pour it into or pour it out of when you want to try a different material.
Yeah. Mm-hmm. And the sorbent is not infinitely reusable. So at some point it will lose its ability to absorb and you'd want to swap it out even with the same stuff.
Mm-hmm. That's right.
It'd be cool to have a thing almost like a gumball machine, when you turn it and then the stuff comes out, or like when you feed a gerbil, actually, like a little trap door, you can empty it and then, pour it in on top through a different hole or something.
Oh, yeah.
I think it's something like Connect 4 where you just pull a slider in the whole
Yeah, exactly. Right. Yeah, that would be great. We should do that. All right, cool. So those seem to be things certainly within the range of, yes, we know how to optimize, particularly the sorbent, and these seems like we could see improvements if a future builder with our advice takes these steps. Anything else that we'd say that is pretty fundamental that we would do on a next build to get any form of improvement?
I've got a couple more.
Yeah.
A tighter box. This one was, I think, the perfect design for starting out because it is an off-the-shelf filter duct that you could buy online and have it shipped in a couple of days for commercial and home use. But it is it's not designed to be a vacuum chamber. And as I mentioned, if you want to get the most efficient carbon dioxide capture, you need to actually provide a significant vacuum. And you can see here in the corner there are little leaks, and it's kind of impossible to really seal this up. We haven't actually tried pumping a vacuum in from it because we didn't have the equipment, but I suspect that it would leak significantly. And also, we were surprised when we took it out of the box to begin with that it was a lot lighter than we expected. And I'm concerned that if you were to try and apply a vacuum inside it, it would collapse like a soda can. Mm. So we never got to that point. There are things called vacuum chambers that are designed to hold a hard vacuum, but the ones we looked at were out of our budget. So that's something where we could use some advice or somebody that's creative to figure out how to build a sorbent chamber that can handle a vacuum. It might just involve bending sheet metal, making it yourself.
Just like a thicker sheet of metal as well?
Yes.
Yeah, okay. Because that shape there doesn't look like the most complex thing. So, it could, I guess, be something that would be custom fabricated. We like the idea of avoiding that and being able to just sort of buy an off-the-shelf part, but we can look for other parts, or maybe something has to be custom made. What David, could you explain, or Seth, what happens again when you apply a vacuum? That is something, we're ready to order that, the concerns that you just mentioned notwithstanding, but what does a vacuum add to this?
Yeah, so there's two things. One is it makes it easier for the sorbent to release the CO2. So you're going to be able to release it a lot quicker, which means less heating cycle and more energy efficient, which, when we look at DAC in general, and particularly at scale, one of the biggest problems is it's often powered with dirty power. So you're pulling carbon dioxide out of the air, but you're powering it with dirty power. So the less power we use, the easier that'll be to power cleanly and efficiently. The other thing that the vacuum buys you is, right now there's air in that chamber, and we're pulling out, in this case, water vapor, but we're also pulling out CO2 that's being added to this mix of regular atmosphere. And so by pulling that vacuum first, you're going to increase the purity of your CO2. So one, that makes it easier to measure how effective you were. And two, it allows you to do something with it on the far end, right? One of the questions we get a lot for Epiphyte is, well, what do you guys do with the CO2 you've captured? And you have a lot more options if you've got a lot purer CO2. Our goal for this was not to use it at all, right? right? We knew we were just going to release it back into the atmosphere just to see that we could do it. But eventually, yeah, we're gonna want to do something with that CO2.
We have some cool ideas for that I'm not going to mention right now, but a little sci-fi. But yeah, that is an important thing to say. We just wanted to do this one process. The Hello World was to take some carbon out of the air, and then the creative journey will include many different directions. One of them is what do we do with the CO2 to make it a true removal. So just to summarize that one, I guess, David, is use a vacuum, but if you're going to use a vacuum, we got to improve the housing here so that it doesn't implode.
That's right.
Number 3.
Or
Okay,
leak.
cool. All right, let me go back to the slides here. Was there a fourth one?
It's more than that.
All right.
The dampers that we got are electrically controlled to open and close, but again, they're designed for home or commercial use. I think these are called fire dampers that are supposed to shut off your heating system if there's a fire, and they are fairly airtight. They've got to be tight against smoke, but again, I don't think they would prevent leakage in case of a serious vacuum. It's like a butterfly valve there. I think it's what it's called, and it closes against the foam inside, but it's probably not tight enough for a vacuum. And this is the CO2 sensor that we use, and there's another picture showing where it's located. On the input side, it's on the tube of the damper assembly, and on the output side, as air goes from left to right, it's kind of it's a little closer to where the sorbent panel is. And if you look at measurements that were made, say over the course of a few minutes, this red line here is the input side, and the pink line is the output side. And that measurement goes all over the place. And I know certainly the CO2 on the input side should not vary that much. And I think that the sensor is still being influenced by turbulence in the chamber. And we
What
need
would that turbulence be caused by? That's air. That's just from the airflow.
from the airflow. It's not a steady flow. It's, well, turbulent. And so I think this is where we need maybe some help from the vendor of the CO2 sensor, and maybe from somebody who's an expert in air motion to figure out how to get a repeatable and steady measurement of the CO2.
Seth, have you thought this through at all? You're a sensor guy, I know. I don't know if, in addition to what David said, if you had any other guesses to hazard how to improve that problem.
Yeah, I think the airflow isn't my core area, but yeah, I think the turbulence is a big issue. You need to make that consistent, and so that's why they're in the box in the first place, right? That's why the manufacturer recommends there's just a small little hole that the sensor peeks through, and that's to keep the airflow fairly consistent and turbulent. The other thing that it's possible that we're doing, especially when you see those red spikes that kind of they come up and they look like they plateau before coming back down.
Yeah.
Odds are what we're doing there is actually saturating the sensor. So we're giving it so much data, like well, maybe not because it's going off the chart.
It's supposed to go up to 2,000, I think.
Yeah. Okay. So that's not saturated. But
Yeah.
I think there's probably something that we could do. Someone who's a mechanical engineer or has an aerospace background could figure out either some sort of enclosure to go inside the chamber or some way to control the airflow so that it's much more stable going across the sensor. The other thing that I think contributes, and it may not be contributing to the variability you're seeing, but it does contribute to the overall baseline, is the calibration of CO2 sensors. CO2 sensors are hard to calibrate, and they require a lot of time and effort that frankly we didn't put in. We have a very basic calibration procedure to get us sort of a relative level, because that's what we were most interested in, is what is the difference between in and out. But a better calibration sensor procedure to calibrate these sensors would get us better and more accurate readings.
Right, and this has been kind of a frustrating process with these sensors. I would calibrate them just so that they would give the same answer. Say if I put them together, they should, with this in the same atmosphere, they should read the same. So you could calibrate them to read the same, and then the next day you come in and they're not the same anymore. So that was something that we had to spend a lot of time figuring out.
Yeah.
Okay,
And
so
not even, part of the problem was power, right, David?
Yes, okay, that's a different page here. So
yeah,
electronics, there are a few other examples, but basically, so these sensors are designed, well, I used a breakout board supplied by Adafruit that has the sensor on a little board with special connectors called Stemma QT, and makes it a lot easier to snap together a system with these little cables and then you connect it to the processor, and you can make these cables longer, and you can put in repeaters. So these cables provide the power supply to the sensor at 3.3 volts, and it provides I2C connectivity for actually transferring the data. But what happens is these wires are thin, even for the power supply, and then this little breakout board here has a low dropout voltage regulator. So when the voltage actually arrives at the supply pin of the CO2 sensor, it's going to be a little bit less than 3.3 volts. But then if you look at the data sheet for the sensor, it says 3.3 is the minimum required voltage. So we were underpowering it. So I put in some thicker wires to provide the power and ground, and then I bypassed the voltage regulator, so the sensor actually was getting 3.3 volts that it required, and that made it behave a lot better. There's some problems that I didn't show before, but basically it was giving a lot of readings that had no data at all in them, and apparently it was just dropping out and not working at all. So when I managed to fix that, at least it was giving data. The data wasn't necessarily as correct as we would like, but at least it was cooperating. The lesson here is, even though things look like they can just snap together, you need to understand just how it works, and you might need to improve it.
so do we think that the thing there would be moving on to a different sensor, or just speaking to people at the company who might be able to give us some more guidance on how to optimally use it? What do you think the pathway forward for that is to improve that problem?
Well, both. I think we need to understand the capabilities of this particular sensor, but we also need to expand our search and look at other companies' sensors and other models made by this company, Sensirion. We were, again, trying to stay within budget, and we did that. We actually came in under budget, but at the time when we were designing the system, I was trying to come up with the lowest cost models that looked like they would do the job. And so I think we need, I would advise the next builders to look a little farther afield and find, maybe pay a little more for something.
Yeah, sometimes these lower cost sensors can be subject to some other effects, so that you can get more noise on them, which could contribute to some of that variability. They also could be more affected by things like temperature and vibration. So the answer may be going to a more robust or a more robustly housed sensor. It could also be that mounting them on the outside of the chamber was actually causing us problems, and maybe we need to have something that kind of suspends it inside the chamber and not actually touching the side. Right. These are all things that we can get through experimentation and through talking to the manufacturers.
Right. Well, what I'm encouraged by with all these things is very specific things that we're trying to optimize for here, and many of them don't seem like it's an absolute void that we're walking into. That we have some thoughts on probably how we can make some improvements in the next round. But unless you're about to break my heart, David, and there's something that's on the next slide that is truly insurmountable. I don't know.
No, that's it. That's the last slide.
All right. That's not too daunting, I don't think. Well, let's do this here as we wrap up. I mean, again, I want to really emphasize is that, first of all, I know I do this all the time and I embarrass David and the rest of the team, it just was like a joy as a non-engineer and non-scientist to watch this idea, which we've been talking about literally since the beginning of OpenAir. And certainly, David, you and I have been talking about it since your early days of working on Cyan, is to watch it turn from a very basic, almost back of the kind of napkin thing into a physical object that did hello world. And then also now we have a pathway forward of things that we know we want to work on and with other people in other places. And that really is it. I think part of the measure of success here is that as we build it, we want to uncover new opportunities and problems that then we talk to the next builder and say, improve upon these, take it in a direction. This is the kind of knowledge, this is the kind of expertise we need. So I do think this is the beginning of something big and amazing, and it really does trace back to this, sweat, tears, and smarts that you guys poured into it. But from you now, you're about to go on vacation, David, a well-deserved one. We're going to move this to New York. What do you kind of look at when you think of the future of a year, 2 years, 3 years from this? If we are successful in building a community, what are the kind of areas of evolution that you think would be most interesting? And be as sci-fi as you want to.
I just like to see more teams of people building in different locations and building off of each other's improvements. So it evolves. I don't think any one group is going to have all the answers, but with information sharing and short cycles of development that we can have now, I think it can evolve pretty fast.
Yep, absolutely. I love to hear that. And by definition, we don't want one group to work on it. I think it really is about how many eyeballs and brains ultimately apply themselves. And I think that the object we've come up with now is specific and coherent enough, and the problems we need to solve are specific enough that hopefully that's the formula in which we can get people who are watching this and beyond to jump into the fray. What about you, Seth? What would be your dream?
So I'm a software and data guy, so that's what I want to see. Is I want to see the software for this built out and to have a collective data store where we can look at data from these devices from all over the world in different conditions with different optimizations, and really start to run some experiments and understand the process a lot better, so we can say, well, if you're in this sort of environment, these conditions, this is what's going to work for you, and whereas over here, it's something completely different, and really start to optimize and understand how these things really work. And I mean, data is eating the world right now. Used to be software, now it's data. So let's get all that data and put it to use.
Yeah, absolutely. Well, I'll be the zany one because I'm the guy who doesn't actually have to pick up a tool to build it. So I can then dream in wackier directions. We have a couple of other members of our community in Colorado and in Texas who are working on algae-based mineralization with a form of algae called a coccolithophore that naturally produces calcium carbonate. And the idea of at some point, and there's many directions. We want to solarize this. We want to make it more energy efficient. But the idea of actually integrating some form of carbon storage right into this, so that we have a direct air capture machine that is feeding into, some type of fish tank reactor with algae that could accelerate the rate of calcium carbonate production. And then to tie in what you just said, Seth, can we really measure that? Can we come up with an MRV and a measurement system for that? And if we had a fleet of these that were building this all over the place, and we're actually taking carbon out at a very, very small scale, but in aggregate something large, and we're able to track that, then it would be really interesting to see at what point can we qualify for selling carbon removal credits, which could then finance a new round of building more and more machines. So we'll see if we get that far. But it's fun to think about this, and hopefully people who are watching this right now and jump in have their own ideas, because that really is the whole point, is how can we make this as interesting as possible beyond 6 people. So So with that, in the link to this video, people who watch it, you'll see all the links that you need to follow and join and participate in our forum and our Carbon Crowd page, and look at the bill of materials we have on Hackster.io. But again, this is just the beginning, and I want to thank the inaugural Epiphyte team. Seth named it. We have to give him naming rights for it as well, and for all the time that was spent for getting us going on this. But really, really appreciate it, guys, and hopefully people have enjoyed this, and hopefully we'll see some of you join the team. So thanks, everyone.